Hi students. So today we are going to learn about the binary operation, which is the last concept in the chapter relations and functions. So in the relations and functions from the beginning we have learnt the types of relation, the types of function, composition of functions, and how to find the inverse of a function. So all these things we have came across the chapter relations and function. So in this chapter the last concept remaining is that is nothing but a binary operation. So today upon the binary operations, these are the things which are coming under the binary operation, the topics. So beginning the introduction regarding the binary operations, then the definition, operation table, commutativity of binary operation, associativity of binary operation, identity element, inverse of an element. So these are the concepts which are coming under the binary operation. So let us go step by step in each of the concepts. So beginning the intro part of the binary operation. So introduction. So binary operation, the name or the word itself says binary means two. So the any operation which is involved between any two elements. So now what are these operations which are involved between these two elements? For example, the operations like suppose if I take addition or plus, then if I need to add any two elements means then we use the operator addition. Similarly, minus, multiplication, division. So these are the operators which are used to operate between any two elements. So these are some of the examples regarding the operators. Suppose if I need to add three elements, if I need to add three elements, say A, B, C means, then how we are going to use it? A plus B, I will add first these two elements, then what the number I got, I'll add that number with the third element. So this is how we are going to deal with the three or more elements. So at a time binary operation means at a time it is dealing with the only two elements. At a time it is dealing with any operation. At a time any operation is dealing with only two elements, and such type of operations are called as binary operations. So that does not implies that only these four are the binary operations. So binary operation, it might be also max, which is nothing but maximum of any two elements, or minimum between any two elements. HCF, it might be of more than two numbers, but simultaneously we are dealing with the any two numbers. Similarly, LCM, it is also a binary operator. So more than two numbers it might be involved, but at a time if we are dealing with any two numbers. So these are the some of the examples for the binary operators. Binary operators. So now how we are going to write this one binary operation? Suppose if I take any two numbers, say A and B. So I considered any two numbers, say A and B, then the operation involved between these two number is addition means, then the thing what we are going to get is A plus B. So clearly if I took this number A from the set of real numbers, and this number is also taken from the set of real numbers means, then whatever the operation after applying to these two elements, what this number we are going to get, this belongs to the set of real numbers. So you can see here an ordered pair A comma B. So to saying it an ordered pair, what till now we have learnt regarding the ordered pair, this is not like that type of an ordered pair, because in the previous ordered pair what we have learnt is the second element is the image of the first element. So this is what we have learnt in the ordered pair, right? But here B is not the image of A. Here these two are the any two elements from the set of real numbers, and whatever the operation we are involving here, that operation is involved between these two numbers. So here we are taking the two elements from the set of real numbers or from set of any arbitrary set. So it will be in the form of an ordered pair, but this is not the ordered pair what we have learnt in the earlier. Remember that one. Here B is not the image of A. These two are any two numbers from an arbitrary set. So whatever the operation we are involved here, so if I considered operation addition means, then addition is an operation involved between these two elements. So after operating or the involving of this operation between these two elements, what the element we are going to get, it belongs to a set of real numbers. So generally we used to write in this manner. So now let us see whether this binary operation what we have written, whether this is a function or not. So let us check whether this one is a function or not. What does the definition of function says? No two elements or no two ordered pair will have the same first element. So this is what it is saying here. So suppose if I write this operator or this one in terms of a set builder form or in the tabular form, means how it will be. So generally we used to write f is equal to a comma b. So like this way we used to write a general function f from a to b, right, where a is an element of a, b is an element of b. So this is how we are generally writing. Suppose if I write here means plus, here operator it is a plus, and how we used to write, we used to write if a comma b means a comma b comma a plus b. Here the first element, it is nothing but this one, and the image of this element is a plus b. So clearly the domain of an operator or a domain of the function plus, it is a Cartesian product. It is a Cartesian product, and the range or the codomain, it belongs to a normal set, right? Because if we add any two numbers, we are going to get a single number that belongs to any one particular set. So this is how it will be in the tabular form. Now how we can check whether it is a function or not? To checking whether it is a function or not, as I said in the definition, no two ordered pair will have same first element. So here this one is one ordered pair, right? This is the first element, this is the second element. So think it whether if I take any two distinct real numbers and if I use the operator addition, whether that for that two distinct number, whether we are having the different for same first number, whether we are having the same answer. For example, if I take 1,3 means the element we are going to get, it is nothing but 1,3 means we are going to get 4. So for the 1,3 itself, we are not at all going to get any other number. If addition is an operator means 1,3 means 1 plus 3, it is 4. So for same 1,3, we are not at all possible to get any other number other than 4, right? So clearly no two distinct ordered pair. Here if I write it in the ordered pair means 1,3, 4. So like this it will be going to become if I write it in the set builder form. So for the same first element we can't have different image, or 1,3 it cannot have, it is not the means 1,3 cannot have two images. So no, it cannot have two images means what does it is saying? So no two ordered pair will be having same first element, right? So we can say that addition, it is a function. Suppose if I take 3 comma 1 means at that time the sum is 4. 1 comma 3 also means at that time our sum is also 4 if addition is an operator means, right? But like this type function is okay, means for two distinct element we can have same image, but for same element we cannot have two distinct images, right? So it is a function, but this is not possible. Suppose if it was possible means then it was not a function. So this is possible, so this is a function, because we know that like this type is a function, but this is a function, but this is not a function. So this is what it is saying here. So this is an information where we are saying a binary operation, where binary operation is a function. It is a function. Suppose if I take the operator minus means how it will be? It will be from set of real numbers to real numbers to the set R such that a comma b implies a minus b. Similarly for multiplication also how it will be? R cross R to R, where a into b, a comma b implies ab. So like this the binary operations are going to be used for subtraction as well as a multiplication. So if I am going to brief what we have learnt here means, generally here what we understood means operator, how we are going to deal with the any two arbitrary numbers which we have taken from the set of real numbers. So if I am going to take the difference or differentiate, if I am going to differentiate between the ordinary function as well as this binary operation saying it as a function means, clearly binary operation is a function where its domain is Cartesian product. You can see its domain is the Cartesian product, right? But our normal function, if I am saying a function f from a to b means, here our domain was an ordinary, it was an ordinary set, ordinary arbitrary set. But when it comes to say binary operation function means, in that time our domain was a Cartesian product. And in the binary operation, here the function is an operator. Here the function is what? It is an operator. But here the function will be f, whatever the thing here. So here we have considered an ordered pair. Here it does not mean that the second element is the image of first element. It is just an any two arbitrary element from the Cartesian product. So operation is involved between these two elements and we get one element. So this is what the binary operation function is saying. And here we have came across whether the binary operation is a function or not. So generally if I am writing the binary operation in terms of set builder form means it will be in this form. So if I have taken one example to verify that one. If I take any ordered pair like 1 comma 3 or any of the ordered pair and use the operator addition means, the addition involved between these two numbers will give us one number. So for the same element we cannot get different sum like 5, 6. For these two number we are going to get as a sum of these two element as 4 only. So no same element or the same first element in an ordered pair, the same element cannot have two different images. So whatever the element we are going to have, we are going to get one image. So this is a function. Suppose if I write 1 comma 3 means at that time also we are going to get sum as 4, but these two are distinct ordered pairs. So like this type it is possible because two distinct element can have same element as an image. This is a function but like this type of formation, that is same element having two different images, it is not at all a function. So by this we can verify, or we can say that the binary operation, it is a function. So this is what, how I generalized how it we are going to write in terms of multiplication as well as in the subtraction form. So this is an introduction part, or the introduction regarding the binary operation. So the definition of a binary operation, what it is saying with the definition means a binary operation star. So we are calling star means a star might be any binary operation. So a binary operation star on a set A is a function. So this operation on a set A is a function, and how we are going to denote it, star, such that A cross A to a set A, where A is any arbitrary set, and we are going to denote it as star from A comma B gives A star B. So this is how we are going to denote the binary operation. So if I say binary operation in set A means, what does that imply? Star star upon A cross star, such that A cross A to the set A. Suppose if I say binary operation in set of real numbers means, at that time it will be star, such that from R cross R to the set of real numbers. Suppose if I say binary operation in set of natural numbers means, at that time star, such that set of natural numbers n cross n to n. So this is what a verbal statement can be written in the form of a representing or denoting the binary operation. So till now we know there are binary operations like addition, plus, minus, multiplication, division. So these are some of the examples for the binary operators, right? These are some of the examples for binary operators. Now, whether these binary operators, or whether this is applicable for, so the thing is whether these all operations will remain always binary operation, whether this always remains binary operation. Suppose if that is the question means, yes, that will be going to depend, it will be going to depend on which set these binary operations are defined. So it purely depends upon which set it is defined. Suppose if I consider a set of real numbers, that is a set of real numbers. So whether in the set of real numbers, whether all these four operations are defined or not, you can see here on the set of real numbers. So if I take addition on the set of real numbers means, how it is going to be represented, addition from set R cross R to set R. So if I take any two real numbers from the set of real numbers means in the form of A comma B, the sum of that two numbers will be A plus B, and obviously this A plus B will belongs to the set of real numbers. So this is how the addition is going to be defined on the set of R. Suppose if I take subtraction or take minus, that time it will be defined in R cross R to R, and it is given by A comma B to A minus B, because the operation here defined is minus. So if I use the minus between these two elements means, the operation minus between these two means we are going to get an element, the difference between these two elements, which is the difference between these two number. Obviously this belongs to the set of real numbers. Multiplication means what happens, even at that time R cross R to R, I considered any two elements means the multiplication between these two number. So A comma B, it is A into B, it will obviously, this one also belongs to R. So when we say this operator is a binary operation, if we take any two elements from the set of real numbers, Cartesian product of real number, whatever the element which we got here, this belongs to set of real numbers, means at that time we are saying addition is a binary operator on the set of real numbers. Similarly here we have taken the two elements from the Cartesian product and we inputted or we use the operator between these two elements, and what the element we got, that belongs to set of real numbers. So minus, it is also an operator under the set of real number. Similarly for multiplication, so if I take division between the set of real numbers, it will be defined like this. So if I take any two numbers, means then it should be in this form. Whether this one belongs to an whatever the element if it takes, means whether a by b belongs to real numbers, think properly. Suppose if I take b is equal to 0, means a might be any number at that time. Suppose, okay, if I take a is equal to some 3, so 3 comma 0 means what does that implies? 3 by 0. So this does not belongs to real numbers because this one is not at all defined. It is not at all defined. So this, when b becomes 0 with any of the element, whatever might be the element a, if b is 0 means whatever the element we are going to get, it is not at all defined. So in this case, what we are saying, division is not a binary operation under the set of real numbers, because a by b, it is not at all defined or does not belongs to real numbers for every a comma b which is belonging to r cross r. So division is not a binary operation on set of real numbers. Suppose if I consider a set of non-zero real numbers, so set of non-zero real numbers, it is represented by r star. So if star comes, means it is a set of non-zero real numbers. So non-zero real numbers means it is nothing but from the set of real numbers I have removed the 0 from that set of real numbers. So on the set of non-zero real numbers, division is a binary operation because division is defined from set of non-zero real numbers, and whatever the operation, whatever the thing or elements we can take from set of non-zero real numbers, we are going to get a by b, where this one belongs to set of non-zero real numbers itself. Here b will not at all possible becoming 0 because from the set we have removed the 0 itself. So at that time a by b belongs to set of non-zero real numbers. At this time it is a binary operation. Here division is a binary operation on the set of non-zero real numbers. Suppose if I take set of natural numbers, if I take set of natural numbers, right, whether the binary operations or whatever the binary operations which we have seen upon the set of natural, whether it is applicable. So if I take addition from on the set of natural number, it will be defined from n cross n to n. So how it will be, if I take any two elements from the set of natural numbers, operation will be a plus b. Here a is also belonging to natural number, b is also belonging to the natural number. So if we add any two natural numbers, even this one is also belonging to natural number. So clearly addition is a binary operation on set of natural numbers. Similarly, if I take multiplication upon the set of natural numbers, means what happens? Clearly, if I take any two numbers from the set of natural numbers, multiplication between those two numbers or multiplication of any two natural numbers, we are going to get a natural number itself. So This one also belongs to natural number. So multiplication is a binary operation under the set of natural numbers. So now let us see what about this subtraction and division. So it is defined from set of natural numbers to natural numbers. Suppose if I take an element, say 3, 5. Obviously 3 is a natural number, 5 is a natural number. What is the operation defined here? 3 minus 5. So 3 minus 5, it is nothing but what? Minus 2. Whether minus 2 belongs to natural number? No. Here minus 2 does not belongs to the natural number. So whatever the elements we are taking from the natural numbers, for all the elements it is not at all going to be satisfied. So there will be certain ordered pair in the Cartesian product, so that it will be the image of that pair is does not going to belongs to the set of natural number. So subtraction is not a binary operation under the set of natural number. Similarly, if I take division, means which is defined upon the set of natural numbers, means how it will be. Suppose if I take an example 3, 4. What will be the our image? That is 3 by 4. So whether 3 by 4 belongs to natural numbers? No, 3 by 4 does not belongs to a natural number. So there are certain elements upon this Cartesian product where its image is does not going to belongs to the set of natural number. So division is also a not a binary operation on the set of natural numbers. So this is how the binary operations which are defined differs from the set. So when we set of real numbers, addition, subtraction, multiplication is a binary operation under real number, but division was not at all a binary operation under real number. So when I take a set of non-zero real numbers, at that time, or including these three, even division is also a binary operation on the set of non-zero real numbers. When I said set of natural number, only addition and multiplications are binary operation under the set of natural number. But subtraction and divisions are not a binary operation under the set of natural number. So this is how the things are going to be understood. So suppose if you didn't get, means rewind the video, pause the thing and understand it step by step. So now based upon the binary operation, let us understand few questions how we are going to deal with it. So in that first one, show that star from R cross R to R, it is given by A comma B gives A plus 4B square is a binary operation. So understand this statement first. So what it is saying, star such that R cross R to R is given by in this format. So here if we take any two elements from the set of real numbers or from the set of Cartesian product, means upon applying this operator they develop a relation in this form, that is A plus 4 times the square of the B square. So this is how, if we take any two number, first any two means any two numbers from this Cartesian, means at that time first element plus 4 times the square of the second element. So this is the relation which is developed between the any two numbers which are taken from this Cartesian product. So we need to say whether this is a binary operation or not. So what I said in the beginning, star from R cross R to R, it is said to be a binary operation, means if we take any two elements A comma B, and what the element it will be A star B upon applying the operator. So when we say the star is a binary operation, when we take two elements from this Cartesian product and upon applying this operator, whatever the resultant we are going to get upon applying this operator, this should belongs to the set of real numbers, means then at that time star will become a binary operator. So similarly here, whatever the element we are taking from here, the resultant it will be whatever the element that should belongs to the set of real numbers. So what does that statement implies here? Star from R cross R to R, they have defined, and it will be nothing but a comma b. We have taken that two element, and upon applying the star operator, the relation between these two elements will be in this format, that is first element plus 4 times the square of the second element. So this will be the relation between these two elements. Now we need to say whether this one is a binary operation or not. So when we are learning the onto function, so at that time what we think, before writing the statement we used to feel that whether the given function is onto or not. Like that, similarly here also we need to feel whether it is a binary operation or not. So observe here clearly, a, it is taken from the set of real number. B is also taken from the set of real number. Upon applying the operator between these two elements, we got a relation, that is a plus 4b square. Clearly a is also belonging to set of real numbers. B square, if I take square of the real numbers, that is also belonging to the real number. For that, if I multiply 4 means even this term is also belonging to the set of real numbers. Sum of two real numbers is also belonging to the set of real numbers. Clearly a plus 4b square belongs to the set of real numbers for any real numbers which we have taken, right? So clearly a plus 4b square, it will belongs to the set of real numbers. So if you understood, or if you imagined what I have said means, then you can write the statement directly, that is for any a comma b which is belonging to the set of real numbers, a plus 4b square is also belonging to the set of real numbers. Therefore this given operator, it is a binary operation. So this is what we need to show, and we have proved it. So now let us move to the next question. Here what they are saying, let P be the set of all subsets of a given set X. Means P is the power set of a set X. So that is nothing but, suppose if I take set X is equal to 1, 2, 3 means, then what are the power set of set X? It will be nothing but empty set, singleton set, right? So this is only for your understanding purpose I am writing. Then these are one of the, another one is 3, 1, another one is 1, 2, 3. So this is the power set, where power set includes all the subsets of a given set X. So this is what the power set is, right? Whatever the element in the power set, all these elements are set. So elements in the power set is all sets only. So it is the subset of a given set. So clearly if P is the set of all subsets of a given set X, and how they have defined, now we need to show that union upon those power set P cross P to P, it is given by A comma B such that A union B. So that means here what, A is an element from the power set P. So what will be the element in the power set? The element in the power set will be any one subset of a given set X. So if I suppose if I take element A as equal to 1, 2 and B as equal to 1 means, clearly A is the one of the element of P. Here A is one of the element of P and B is also one of the element of P. Clearly A and B are one of the subset of a given set X, right? So how they have defined now? Union from P cross P to P, it is defined in the form of A comma B such that A union B. So we have taken the two elements, and the operation how it was involved means, it is nothing but 1, 2, one set, another one is 1. So what is the relation between this one? A union B. So 1, 2 union 1. What will be the union of these two? It is 1, 2. Obviously, if we take any two subsets of a given set X, that is nothing but the elements which is belonging to the set P means, if upon applying the operator union between those two sets, the resultant means what will be the union of these two set? 1 comma 2 itself, that also belongs to the power set only. So that is what the given statement is saying. It is clear, right? If we take any two, now you need to feel to say it as a binary operation. When we can say it as a binary operation, if we take any two elements from the Cartesian product P cross P, upon applying the operator, the element, whatever the element is there, that should also belongs to P means, then we can say that this given union is a binary operator. Now feel it. Suppose if I take any two element from the P means, then upon applying the operator union between those two elements means, at that time the union between those two element will be the element which belongs to the P itself. It does not go beyond P, means we are not going to get any elements which does not belongs to the set P, right? So clearly union from P cross P to P is a binary operator. Similarly, we can say it for intersection also. So if I take any two sets, similarly I will take here this one on the itself. So what does they are saying? A comma B gives A intersection B, right? So I have taken two elements from the set P cross P. That is, one is A is nothing but 1 comma 2, B is our 1. So what is the operation involved between those two sets? That is intersection, 1 comma 2 intersection 1. So what is the intersection between these two sets? It is nothing but 1, right? So this is where 1, and when 1, it also belongs to the power set P. So if we take any two elements from the power set P, which is the subset of X, then the intersection between those two sets we are going to get as an element or a set which is belonging to the power set P itself, or the subset of X itself. So clearly even intersection is also a binary operation. So here is one of the example. So through this example we are going to explain a binary table. So binary table is through binary table we can say the given operation is a binary operation, but this is applicable only when the set is very small. So suppose very small means up to maximum up to 10 means we can verify the given operation is a binary operation through the binary table. So here they have given one of the example. Show that V from A cross A to A is given by A comma B such that maximum of both elements, and wedge from A comma A cross A to A is given by the minimum between those two elements. We need to show it as a binary operation where our set A is 1, 2, 3. So we need to draw a binary table. So how it will be the binary table means, so I'll do with first V. So V is the binary operation. So here the row, it will be our A element. So what are the possible elements from the set A? We can take 1, 2, 3. And the column elements, I will call this one as a B. So what are the possible elements which we take for B? It is 1, 2, 3 itself. So all possible ordered pair is possible with all these boxes, that is 1 comma 1, 2 comma 1, 3 comma 1, 1 comma 2, 2 comma 2, 3 comma 2, 1 comma 3, 2 comma 3, 3 comma 3. So this is all the possible ways of A comma B with the elements from the set A is possible within this boxes. So now each box, what does that represents means, suppose if I take 1 comma 1 means, what does that represents? Maximum of 1 comma 1, right? So that is nothing but 1. What is the maximum between these two? So 1 comma 1, what is the maximum? 1. 2 comma 1, what is the maximum? 2. 3 comma 1, what is the maximum? 3. 1 comma 2, which is the maximum? 2. 2 comma 2, what is maximum? 2. 2 comma 3, what is maximum? 3. 1 comma 3, what is maximum? 3. 3 comma 2, what is maximum? 3. 3 comma 2, 3 comma 3, which is maximum? 3. So now you can see here whatever the elements which I have got through using this operation V, you can see the elements. All these elements belongs to the set A, right? So clearly V from A cross A to A, it is a binary operation. Similarly, you can do for wedge. So this one is for do it by yourself part. Try to do that one by yourself through the binary operation table. So here the agenda, it is clear that whatever the elements we are going to get within the table, if that elements belongs to the given set itself, means then it is a binary operation. So this is what a binary table is going to be say, or how we are going to prove the given operation is a binary operation through the binary table.